Hello, welcome. In this part, we will discuss an important limit theorem, which is extremely useful in applications. This theorem is commonly called the squeeze theorem, also called the sandwich theorem. Let's have a look at the statement of this theorem. Let a sub n, b sub n, and c sub n are sequences of real numbers for which there exists some positive integer such that a sub n is smaller or equal to b sub n, which is smaller or equal to c sub n. Meaning that the nth term of the sequence b is in between the nth terms of the sequences of a and c. If it is true for all indices n larger or equal to n sub 0, and that the limit of a sub n as n approaches infinity equals to the limit of c sub n as n approaches infinity equals to L, then the sequence b sub n converges and the limit of the sequence b sub n as n approaches infinity also equal to L. So this simply says if the nth terms of the sequences a and c are approaching a fixed number L as n approaches infinity, then the sequence in between also approaches L. Let's have a look at the proof of this theorem. Let epsilon be given. Since the sequence a sub n is convergent, there exists some positive integer n sub 1 such that the absolute value of a sub n minus L is smaller than epsilon for all indices n larger or equal to n sub 1. Similarly, since the sequence c sub n is a convergent sequence, there exists some positive integer n sub 2 such that the absolute value of c sub n minus L is smaller than epsilon for all indices n greater than or equal to n sub 2. Now we define the capital N as the maximum of these indices n sub 0, n sub 1, and n sub 2. Then we have from the first inequality here, which says the L minus epsilon is smaller than a sub n smaller than L plus epsilon. So we have copied this inequality here, and then we use the hypothesis that a sub n is smaller or equal to b sub n, which is smaller or equal to c sub n. And then from this inequality we can write L minus epsilon is smaller than C sub n, which is smaller than L plus epsilon. Then we can copy this part of this inequality here. Therefore, the left-hand side is written here, and we take the sequence B sub n here, and we copied L plus epsilon here. So for all indices n greater than or equal to the upper n, L minus epsilon is smaller than B sub n, which is smaller than L plus epsilon. And this can be put into this form. The absolute value of B sub n minus L is smaller than epsilon. And this is true for all indices n greater than or equal to n. So we proved that for every epsilon, a positive real number, there exists some n such that the absolute value of B sub n minus L would be smaller than epsilon whenever the index n is chosen to be equal to greater than or equal to n. By definition, this proves that the sequence B sub n has limit L as n approaches infinity. This concludes the proof of the squeeze theorem. Please pause the video and try to read the proof again. Let's have a look at an example. Apply the squeeze theorem to show that the limit of sine of n over n equals to 0. Let's have a look at the solution. Since for all positive integers n, sine of n is greater than or equal to -1 and smaller than or equal to +1, so we can divide this inequality by n, since n is a positive integer. So we obtain the inequality shown here. Now we identify -1 over n as a sub n and sine of n over n as b sub n and 1 over n as c sub n. Since the limit of a sub n equals to 0 and the limit of c sub n also equals to 0, by the squeeze theorem, the sequence of terms in between, which is the sine of n over n, also equal to 0. Let's try to plot the first few terms of the sequence sine of n over n. In this figure, the sequence a sub n is plotted in the violet and the sequence c sub n is plotted in red, and we see that the sequence of terms sine of n over n is squeezed in between the sequences a sub n and c sub n. So since a sub n and c sub n are approaching 0, by squeeze theorem, the sequence of b sub n will also approach 0. Proposition. Let a sub n and b sub n be sequences in real numbers with b sub n is greater than or equal to 0 for all indices n. Also suppose that there exist real numbers a and m, which is a positive real number, and a positive integer n sub 0 such that the absolute value of a sub n minus a is smaller than or equal to m times b sub n for all indices n greater than or equal to n sub 0. Now if the limit of b sub n equals to 0, then the sequence a sub n converges, and the limit of the sequence a sub n is equal to a. So this number is the limit of the sequence a sub n if the sequence b sub n converges to 0. Please try to prove this proposition.